Okay, for Unit 9, we're going to look at hidden Markov models and particle filters and tie this into robotics. We'll start with some resources from the Stanford lecture series. We'll start with the normal ones we've been looking. Unit 11 uh, talks about hidden Markov models and particle filters. So we'll jump into that and listen to Sebastian introduce this.
Well, today I have the great pleasure to teach you about hidden Markov models and filter algorithms. The reason why I'm so excited is in pretty much all of my scientific career, hidden Markov models and filters have played a major role. There's no robot that I program today that wouldn't extensively use hidden Markov models and things such as particle filters. In fact,
Okay, so Sebastian is excited, and I'd have to agree with him here. Some of the material we're going to cover this unit is some of my favorite material in artificial intelligence, in particular particle filters. So we're going to jump into that. Now, I'll highlight certain areas for you to look at here. We want you to watch videos 1 through 5, particularly. This introduces this topic of hidden Markov models and robotics and localization here. So 1 through 5 go over that, and then 5 ends with a quick introduction to Markov, what a Markov chain is.
So let's begin by taking the hidden out of the Markov model and study Markov chains. And you're going to use an example for which I will quiz you. Suppose there's two types of weather, rainy, which we call R, and sunny, which we call S. And suppose we have the following state transition diagram. If it's rainy, it stays rainy with a 0.6 chance, but with 0.4 it becomes sunny. Sunny remains sunny with 0.8 chance, but moves to rainy with 0.2 chance. This is obviously a temporal sequence, so the weather at time 1 will be called R1 or S1, at time 2 R2 or S2. So suppose
Okay, so he introduces Markov chains here. Markov chains are sequences of states where the next state is dependent only on the current state, not on a whole history of states. And this is a common modeling technique. We've seen something similar with finite state machines when we first did that at the beginning of the course. But he goes into some of the statistics of Markov models and chains that are kind of beyond what we can do in this course. So we're going to skip over a number of these until we get down to his section where he introduces the hidden Markov models and the happy grumpy problem. And so again, that's down here 17 through 19. We want you to jump down after 5, jump down to the 17 and 19. And that's here I'm going to introduce this.
So now let's return to hidden Markov models, and those are really the subject of this class. Let's again using the rainy and sunny example just to keep it simple. So these are the transition probabilities as before. And let's assume for now that the initial probability of rain is 0.5. Hence the probability of sun at time 0 is 0.5. The key modification to go to hidden Markov model is that this state is actually hidden. I cannot see whether it's raining or it's sunny. Instead, I get to observe something else. So suppose I can be happy or grumpy, and happiness or grumpiness is being caused by the weather. So rain might make me happy or grumpy, and sunshine makes me happy or grumpy, but with vastly different probabilities. If it's sunny, I'm just mostly happy, 0.9. There's a 0.1 chance I might still be grumpy for some other reason. If it's rainy, I'm only happy with 0.4 probability, and with 0.6 I'm grumpy. In fact, living in California, I can attest that these are actually not wrong probabilities. I love the sun over here.
Okay, so he introduces this idea, and this is critical to hidden Markov models. The hidden part is that there's some Markov model here we can't see, and we can observe some situation here. So, for example, let's say we weren't in California. We were just checking in with Sebastian every day, and all we could tell was if Sebastian was happy or grumpy. We didn't know the weather there. We couldn't just look outside the window. And so looking at this chain of happy and grumpies, we'd have to figure out if it's rainy or sunny based on that. And that so 17 to 19 goes over that, and it's a good introduction without getting too much into the statistics. Then we're going to leave that. In the assignment, we'll have you talk a little bit more about hidden Markov models. But we won't, again, be able to go into too much detail. We'll get back to them a little bit when we get to language in a future unit. Then we're going to jump into robot localization. This is figuring out where a robot is and looking at particle filters. And this is the key part of this that we want to work on and that we'll be looking at for the assignment is this particle filter example. We'll be running code that's very similar to this particle filter example code here in Java for the assignment. And you'll find more details here. But certainly watch these videos, again, that 24 through 26 set down here. Here you might, yeah, 21's a good one. I have that on the list too that talks about localization. Now I want to jump to another course. This is a more advanced course, online course that Sebastian teaches on robotics and AI. And I want to jump more into this particle filters and programming those. In the intro course at Stanford, they don't give you enough detail of particle filters to really implement them. So we're going to look at this just one unit, unit 3 from this more advanced course. And we're going to look at certain videos in this. So this is all in unit 11, and we're going to look at, all in unit 3, and we're looking at videos 11, 12, 19, and so on. So let's jump there and look at those. So in this playlist from the CIS Sanford or Udacity 373 Robotics and AI course, we're going to skip over a lot of this material. It just goes over some other strategies. And we're going to get down to unit video 11 here and look at this. And the first part talks about different strategies, and then we get into particle filters about
and see a
120.
particle filter in action. So here is a floor plan of an environment where a robot is located, and it has to perform what's called global localization, which is it has no clue where it is and has to find out where it is just based on sensor measurements. This robot has range sensors as indicated by the blue stripes. Those use sonar sensors, which means sound, to range the distance of nearby obstacles. And it has to use these range sensors to determine a good posterior distribution as to where it is. But the robot doesn't know it's starting in the middle of the corridor. In fact, it is completely uncertain as to where it is. Now the particle filter represents this using particles. Each of these red dots, of which there are several.
Okay, so Sebastian will run you through particle filters. It's a really interesting process, again, where we'll create these random dots and set it up. And in the assignment, we'll do a simple thing. We use the same method for driving and localizing the turtle bot. So we've got a map of Tower Hall at St. Scholastica like this, and then we'll simulate the robot driving around, and your job will be to program some of this part into the robot. So I want you to watch some of these videos here. So part of 12, this part of 11 and 12, 18 and 19 go over some of the details of this. So again, 12 just introduces you here, but once they start going into the code, Sebastian has different code that uses Python. I've translated this all into Java and then changed it to fit a little different method here. So once he starts talking about the Python code, we're going to skip over all those parts. And then you can jump back in at 18 and 19, where he's talking more about this robot world and the sensors, and then particularly how particles are created and solved. And again, we'll jump back into this with the assignment, because your assignment will have to do with this stuff. So the key concepts is to understand what a hidden Markov model is, and then what are particle filters. Now around campus at St. Scholastica, I work with a TurtleBot robot. I'll see if I can post a video of it here with one of our students. Right now my students are working with it. I've had students trying to add voice navigation to it. It's got a LiDAR sensor on it, and it can drive around the building quite well. But here's an introduction to the Turtlebot, what it looks like. It's just a small robot. Here it has a Kinect on it from Microsoft. We've also added a little more advanced LiDAR unit to this for better navigation. And this uses an operating system called ROS, or Robot Operating System. This is used to run many of the robots around the world. Use this ROS operating system. So you might want to look a little bit at this setup, and if you're really interested in robots, ROS is the way to go. We're not going to be able to go too much into using ROS here. One of the problems with ROS is we need an Ubuntu system. So you need to set up a computer that boots that flavor, Linux, and then you have to install ROS on top of that. So it's a little challenging to get set up on the remote systems or for online students. So we're not going to play directly with ROS, but I want you to read a little bit about it here. Particularly two things, two concepts you should be aware of is one is localization. Again, Sebastian talks about that. And again, that's using sensors to recognize where the robot is. And again, our robot uses either a Kinect or a LiDAR unit that spins around to recognize where it is. And when we get into talking about autonomous cars and self-driving cars, we'll bring both of these up again, localization. Now, SLAM is what's called simultaneous localization and mapping. The robot has to drive around, and sometimes it'll drive around with a fixed map and just know where it is in the map. Another thing that's challenging for the robot is drive around in a new environment where it drives around and creates the map, but also keeps track of where it is in its own map, and that's something called SLAM. And that's an area where Sebastian has done a lot of research on. So that's your basic starting point here. So our next unit will deal more with robots in general and looking at robots. We'll talk more about the ROS system and other AI-related topics in robotics in the next unit. But this gets us started with localization and particular particle filters and hidden Markov models.